Hello everyone. In this video we are going to talk about three-dimensional elements. I told you about three-dimensional elements in one of my ANSYS videos, right? Specifically tetrahedron and hexahedron and two other elements, but here we're going to mostly focus on tetrahedron and hexahedron, and for formulation we're going to use the simplest one, tetrahedron. So a tetrahedron, as you know, it has four faces, four nodes, and four mode shapes. And here, since the problem is 3D, so each one of these nodes has 3 degrees of freedom, right? Remember in 2D when we have the triangle, we had 2 degrees of freedom, U and V. Now here we have 3 degrees of freedom, U, V, and what? W, of course. So these are those 3 degrees of freedom. And we're going to write them based on the nodal values, which are UI, UJ, UK, and UL, and similar things for V and W. And here I call my nodes basically I, J, K, and L. The other thing you have to pay attention to is that the mode shapes that we are using for U, V, and W are the same, S1, 2, 3, and 4. And the definitions of S1 to S4 are here written based on the coordinates of the points in absolute frame or in global frame. And there are 4 coefficients that each one has, and these coefficients are different from the other mode shapes. So overall, there are 16 coefficients plus a volume of the element, 17 numbers that we have to calculate if we want to get to the mode shapes. And the volume, or 6 times volume, basically comes from a 4x4 determinant, right? Where you have 1's, x's, y's, and z's. And then here, if we focus on the coefficients for the first mode shapes, right? A1, B1, C1, and D1, or you might call them AI, BI, CI, and DI, they are coming from what? They are coming from 3x3 determinants where the A, the constant term, is determinant of basically x, y's, and z's, right? Which is only between j, k, and l, and basically it's kind of the surface area of this object, probably times 2. And then B, if you look at B, your x column is replaced by 1's. Why? Because this B is multiplied by A, and by x, and so the x columns are gone, replaced by 1, and you also have a negative. When you go to C, since C is multiplied by y, the y columns are replaced by 1's, and again this is 1. And then when you go to the coefficient of z, which is d, the z column is replaced by 1, and you have a negative 1. So basically they are switching from plus to minus to plus to minus, so it's like a negative 1 to the n, right? When n is the number of that coefficient, 1, 2, 3, and 4, or n plus 1 in this case, actually. So you switch between positive 1 and negative 1. And if you say, okay, what about the j coefficients? What about the k coefficients or l coefficients? Where they are the same thing as these I coefficients, except you rotate between I, j, and K and L subscripts. For example, if I want to find A, J, right, what do? If you look here, I still have X, Y, Z, but what happened? If you look at the order here, what is the order? The order is, as you go from top to bottom, you go from J to K, and then from K, you go down to what? L. Remember, since these are I coefficients, there will be no I information in any of them. Now here, these are J coefficients, so there will be no J. It's going to be I, K, and L. But look at the order here. It's K goes to L, and L goes to I, right? So my coefficients are these, my nodes actually, I, J, K, and L. This time for I coefficients, what was the order? I went from J to K, K to L. That was the order, right? Because this was the focus. Now this time, this guy is the focus. So what is the order here? the order is, since J is gone, I start at K. I first go from K to L, and then I go from L to I. You see? And that's the order that you have the data in the rows. And then again, when you go to B, then the X data is going to be replaced by ones plus a negative behind the determinant. When you go to C's, then the Y columns are replaced by 1. Then for D, the Z columns are replaced by 1. And again, you're switching between negative and positive one at a time. And just as one more example, if I want, let's say, a K, right? I want a K. What determinant is that? Well, look at here. Here, my focus is going to be K this time. So what am I going to get? So the focus is here at K. So I should start at L, right? And if I go at L, there is nothing here, so I should go back. So first I go from L to I, and then go from I to J. So the data here are going to start with L. So XL, YL, and ZL. And then I start with what? With X of I, Y of I, and Z of I, and finally X of J, Y of J, and Z of J, right? And so on and so forth. And again, I replace the columns with ones and add the negative minus 1. So this is how you find the coefficients. This is how you find the mode shapes. And once you have the mode shapes and the nodal values, these U's, V's, and W's for the nodes, you can find U, V, and W anywhere inside the element, okay? So this is the mode shapes for tetrahedron. And now if you have basically any other physical quantity here that you want to describe, let's say instead of U, V, and W, you are looking at temperature distribution, right? So these tetrahedrons are used in a 3D problem of heat transfer. Then how would you write T at any point? So what is T at any point inside this for which the coordinates are X, Y, and Z? Well, you say T is what? Is T at basically node I times S1 plus T at node J times S2 plus T at node K times S3 plus T at node L times S4, right? And similarly, if there are any other physical quantity, right, you just use these 4 mode shapes and multiply by the nodal values. So this is how you use a tetrahedron, okay? Now, if you have hexahedron, the cubic element, it has 8 nodes, of course, the linear one. Here we are talking about a linear one, so let me add that for you here. So this is a linear tetrahedron. We have a basically quadratic tetrahedron, right? Where the quadratic, you have one basically node in the middle of each one of the edges. So that guy has how many? It has, as you can see, 10 nodes, a quadratic one. So here we are also talking about a linear hexahedron, the simple one. And this one clearly has only one node at the corner, so it has 8 nodes and 8 mode shapes. But again, we also have the quadratic one where you have one node in the middle of each edge. So that one has basically 20 nodes here, okay? That is more complicated. So here we are only looking at the simple ones, right? Now, for this case, it is easier to write it in terms of the natural coordinates instead of the global coordinates. Remember, for triangular elements and tetrahedron, which is like the 2D version of that, it's always easier to use global coordinates. But for the quadrilateral and the 3D version hexahedron, it's easier to use the coordinate at the center, right, which is natural coordinate. And here we are showing it with R, S, and T, right? For sometimes we show them with as Kc, lambda, and eta. These are the same thing. So here I'm showing you the mode shapes as well as what? As well as the nodal values. So here, if you have 3 degrees of freedom at each node, U, V, and W, in general, you have to write U as what? And here you call the nodes what? You call them I, J, M, N, K, O, P, and L. So it's like U at I times S1 plus U at J, S2. And let me add them for you. So it's the combination of these 8 nodal values and the 8 mode shapes, right? And here you can see the nodal values. And whatever is multiplied to each one of them are these mode shapes. So for example, S1 here is what? S1, the first mode shape, is what? Is this guy here? Of course, times 1 over 8. So it's 1 over 8, 1 minus S1 minus T1 minus S1. And here the small s and capital S are different things. Okay, capital S is the mode shape, small s is one of the coordinates for the natural frame. Okay, so, and again, these mode shapes have the same properties that we had in the past, right? For example, here, if we look at node I, right, here, what is the coordinate of node I? What is R, S, and T for that? Well, as you can see, it is in the negative side for all of the 3 coordinates. It's negative T, negative S, and negative R. So it is R equals S equals T equals -1 for that. And if I plug them here, it's 1 minus 1 for all of them. So it's going to be 2, 2, and 2, which the product is 8. 8 divided by 8 is 1. And if I plug in the values of coordinates for any other node at this function, one of the coordinates for one of these 7 other nodes is 1. So the whole product is going to be 0. So you clearly see that each mode shape is what? Is clearly a 1 at its own node and 0 everywhere else. And that way you can easily find these mode shapes. You don't need to memorize anything. And similarly, all of these, you can clearly see that the mode shape is going to give you 1 at I, and then for like S1, and then at J, K, and L, it's going to give you a 0. For example, if the node is at I, then for X, Y, and Z, you have to plug in X, I, Y, I, and Z, I in here, right? And what is it that you will get? Well, you have all of these determinants multiplied by X, I, Y, I, Z, I, and plus A. And then you have to simplify this whole term, right? So here it's a lot of algebra involved, but you can show that if I plug in X, I, Y, I, Z, I and calculate and expand these determinants, you can do it as a practice on linear algebra and determinants. You can show that this entity is going to be 1. Everywhere else, it's going to be a 0. Okay? And it's a little bit harder to show for the mode shapes of tetrahedrons, but you can show that. So these are the mode shapes for what? For U, and then the exact same mode shapes are used for what? V and W, except the nodal values are changed for V and W here. Okay? So this is your 2 important and simple 3D elements. As I said, there are higher orders, there are other elements, prisms, and so on. But here we just want to have the video short. Therefore, we just stop at looking at these. And here I'm going to use one of these, which is tetrahedrons. And I'm going to use these linear tetrahedrons and show you the analysis of 3D solid mechanics problems. So again, let me add the word linear here. So remember when we did 2D problems, we used the minimum potential energy formulation. We're going to use the same thing. Remember, potential energy, or strain energy actually, not potential, strain energy here is, because potential is this term minus the work done on the external forces. So the strain energy is 1/2 integral over volume of sigma transpose epsilon dV, where sigma is the new matrix times epsilon. New matrix for 3D is this matrix here, and epsilon is basically the derivatives of U. Components of epsilon are derivatives of components of U, V, and W. In this case, therefore, your epsilon can be written as a B matrix times U. Remember, we did the exact same thing for 2D. And the B matrix in this case is this matrix here, okay? Where these numbers inside the B matrix, these A's, B's, C's, and D's are exactly these A's, B's, and C's that we found here. So once you calculate these A, B, C, D's, you can easily form matrix B, and nu is only two single numbers for isotropic material. Therefore, with the exact same formulation that we had in 2D, K is going to be V B transpose nu B, where V is the volume of the element, B transpose nu B. And it's going to be a big matrix, a giant matrix, and here we have not expanded it, but you can basically perform that numerically, or you can use MATLAB symbolic or anything and find this giant matrix. And when I say giant, it doesn't mean the size is giant. The size is going to be 6 by 6, but the components are going to be lots of symbolic parameters. And similarly here, if I have a distributed load on the surfaces, right, then I can go ahead and find the equivalent load matrix for that. So here, if the load is on surface ijk, then I divide the area of that surface by 3, and then I plug in px, py, pz all the way down, and 3 zeros, where p equal px, py, pz is what? Is basically the distributed load density on that surface. So let me show you a picture of that, or draw a picture of that maybe here to make it more clear. So if this is my object here, the load is applied to what? The load is applied to this surface here, right? So it is a load like this that is applied everywhere on this surface, okay? On the surface ijk, it is applied everywhere, and this guy here is your P, where it has 3 components, Px, Py, and P. Z, and this is going to be what? Your equivalent load. Now you might say, what if the force is applied to the other surfaces, or what if the force did not have a y or z component? Well, if it didn't have y or z component or x component, just set them to 0 in this formula. But if it's applied to another surface, how do I change this formula? Where here I refer you back to my previous formulation on 2D elements, right? Where we had the same thing, but this time it was edges, right? So it was here, I assume, that we had this. Remember this guy? Look at this. Let me just copy this for you. So you can derive it on your own. You don't need me to help you on that. I'm sure you know it better than me. But this is what we had basically last time. So if it was applied to what? To the IK edge, then this was my what? My equivalent load. If it was applied on IJ, it was this. If it was applied on JK, it was this. So basically, if the top 2 numbers are I, the second 2 numbers are J, and the last 2 numbers are K, right? Here, J index is missing, so I plug in 0. Here, K index is missing, so I plug in 0. Here, IJKL, there is L, but L is missing, so I put 3 numbers, 0 for L. So for instance, if it was applied on another surface, let's say here on IJL, right? So if it was on IJL, what would you do? What is your formula here? So it's going to be area of IJL divided by 3. And then here you have this 12 by 1, where since the first 3 are I, the second 3 are J, the next 3 are K, and then the last 3 are L. Therefore, which one should go to 0? Well, of course, K. So you will have Px, Py, and Pz. Again, Px, Py, and Pz. You will have 3 zeros, and then again you have Px, Py, and Pz. Z, right? So, and similarly, you find two other ones for the two other surfaces. So this way you can find your equivalent load matrix for different faces. And if it's a concentrated load on any surface, then basically on any node, actually, if it's any concentrated load on any node, then basically the component of that will only be applied on that node, or if it's on other nodes or anything, right? So if it's just on node L, then the L components are non-zero in general, and then ijk's could be zero or anything for that matter. And that's the equivalent of this Q matrix that I showed you in my previous lecture. Remember this? Right? So this was a concentrated load that could be applied to all three nodes in general, which is typically not, because if it's concentrated, it's only on one of these nodes, really. So two of them will be in general, could be non-zero, the other four could be zero. In our case here, then we have basically the Q can have three components and you have four nodes, so the Q matrix is going to be 12 by 1. And then out of those 12, 3 of them in general, depending on which node the force is on, could be non-zero, everything else is 0. Okay? And here I did not go with an example, and the reason for that is it is going to involve a ton of calculations, and it is going to involve some 3D geometry and breaking a volume into tetrahedrons and so on. So an example of that is just a tedious work here and showing a lot of numbers and giant matrices. So I'm sure that for this part here, you can solve examples by hand, but you would rather do it with ANSYS or with an FEA software. Therefore, I leave this part to you if you want to practice it with ANSYS, right? Break a volume into tetrahedrons and apply some load and look at the numbers here. But this is the basics that the software is using behind the scene. So thank you so much for your attention. I will see you in my next video. Thank you.